Hello and welcome to AC Practice Knowledge Assessment T1 through to T7, and this is part 3 of 3. So I've broken up the video into 3 smaller chunks, making it a little bit easier for people to handle. So just as a reminder, each of the questions is made up of 4 slides. The first slide is the question or the problems posed. Then I give you an opportunity to pause the video so you can try and solve the problem. Then we continue on to the pause hint screen. Again, you pause the video after I give you the hint and continue with your solution. And then after you bring it off pause, I will then give you the answer and explain why it is the answer. So hopefully that will be helpful. So here's question 21 in our series. Which components are capacitive? So in this circuit, which components are the capacitive components? So we'll pause here while you think about it. Hopefully you didn't need too much time to think about it. So here's the hint. So it's all about the symbols that are used. So this is a circuit diagram. So we've got to think about the symbols and what they represent. So which ones are the capacitors? Let's now move on to the answer. So the answer is C and E. So these ones here, capacitor symbols. They may be reasonably rough capacitor symbols. I'm not too good at drawing in PowerPoint, but they're the ones. So capacitor symbols. This one over here was an inductor. So this was an inductor. And over here, we'd have to think this one was a resistor of some kind. So question 22. Compared with a resistor, what is the current limiting characteristic of an inductor? So compared to a resistor, what is the current limiting characteristic of an inductor? We've got 4 choices: frequency, supply voltage, supply current, or maybe all of the above. So pause here while you think about it. So let's go to the hint now. So here's our hint. Think of the formula for inductive reactance. Then think which elements in the formula would be the ones that, compared with a resistor, are going to do the current limiting. So let's now move on to the answer. The answer is frequency. So if you remember, the formula is 2 pi fl. So the only option we had there was that would fit in that formula was frequency. Therefore, supply voltage could be eliminated, supply current could be eliminated, and it certainly was not all of the above. So even if you were just using process of elimination, they could all be eliminated, and the only one you're actually left with was frequency. Question 23 now. Determine the total impedance of a parallel RLC network. Which parameters are required? So we have a list of parameters here: the total reactance and the power factor, the total current and resistance, the supply voltage and the total current, or the capacitive, the resistance, and the inductive reactances. So let's pause here while you think about it. So welcome back. Let's go on to look at the hint. So the hint we're going to drop for this one, it's all about Ohm's law. So when it comes to impedances and all those kinds of things, how can we use and what can we use to work out impedances and how it applies to Ohm's law? Which ones of these fits? So pause here if you need to have a think. So let's now move on to the answer. So here the answer is the total supply voltage and total current. So that is the trick here is the supply voltage and the total current. So the reactance and power factor had nothing to do with those. We can eliminate that. Total current, yes, we do need total current, but we need to consider far more than resistance in a parallel circuit. There could be other currents involved, so that one had to be eliminated. And capacitive, resistive, and inductive reactances will play their part, but it's not enough information to be able to get to the impedance. The only way we can get to the total impedance is using the supply voltage and the supply current. So question 24. Here we've got to calculate the branch currents in an RLC network. It's going to take a little bit of time. So have a think about that. Calculate the branch currents in this RLC network. We've got 220 volts at 60 hertz, a resistor at 65 ohms, a capacitor at 35 microfarads, and an inductor at 200 millihenries. So a pause here. This will take you a little bit of time to calculate out. Okay, let's move on to the hint. So the hint is you've got to do Ohm's law after calculating the reactance in each branch. So we need to be thinking about how do I calculate the reactance in the resistor, the capacitor, and the inductor, and then use each of those and Ohm's law to work out the current. So again, pause the video here if you weren't on the right track and have another go at the problem. Okay, let's now continue on with the answers. So you can see here, I'll just turn my pen on. The resistor, you don't have to work out the impedance because the impedance in the branch of the resistor is the resistance. So IR, the current in the resistor, is simply the voltage divided by the resistance. So 220 divided by 65 is our 3.38 amps. So we're going to end up with a current of 3.38 amps through here. Remember, it's alternating current, so the arrows go in both directions. The next one is we need to work out the capacitive reactance. They've told us the capacitance, but not the reactance. So we need the formula 1 on 2 pi fc. And if we punch our values in, we'll get a reactance of 75.8 ohms. We use that to calculate the current, so our 220 divided by our 75.8 gives us 2.9 amps, so we're going to end up with 2.9 amps in that branch in here. And then finally, we've got to work out the inductive reactance, 2 pi FL, and that gives us 75.4 ohms. And again, using Ohm's law, V on XL, 220 volts divided by our 74 gives us 2.91 amps. Very, very close, very, very similar. moving on to question 25 now. Examine the phasor diagram below. What is needed to determine the power factor? So study the phasor diagram and have a look. What would you need to determine the power factor? So pause here. Well, welcome back. Let's have a look at the hint that we're going to give you. So, which angle is required in relation to the reference? Remember, when we're determining the power factor, it's going to be in relation to the reference. So again, if you haven't been thinking which angle is something in relation to the reference, then you need to pause here and have another think. So let's now continue with our answer. The power factor is the cos of the angle between the reference and the total current. So let's examine our diagram. This is the reference. It's pretty obvious. It has the word ref in it, therefore it's the reference. I total is the total current. So you can see here we've got a capacitor with current, an inductor with current, and a resistor with current. And we've done a phasor addition here of IR and IC, and then we've added those two together to end up with this one here, I total. Therefore, the current I total in reference to the thing is this angle in here, and that's the one that's been labelled theta. So theta is the one that we would require because we would need the cos of that angle. So the cos of the angle there is going to equal our power factor for this circuit, and here you can see the current is lagging the voltage, so we're going to have a certain number of degrees and it would be lagging. So again, examine the phasor diagram below, and what does the symbol theta L represent? So examine the phasor diagram. What does the symbol theta L represent? Pause the video and have a think. Okay, let's move on to the hint. The required angle is not at 90 degrees. So if you have a look at discovered where theta L is on the diagram, you'll note it's not at 90 degrees. So what device might cause this? What device might have multiple elements in it that would cause this? So let's move on to the answer. So the answer in this case, it's an inductor. The label, first and foremost, should have probably given it away. Theta L means the angle in the inductor, and here it is here. So theta L, and it was this angle all the way through there. That's the angle theta L. And the only thing that has that arrangement would be the inductor, because an inductor is made up of a resistor and an inductor in series. Hence, we didn't end up with a nice 90 degrees down here because of this resistive component in the inductor. Moving on to question 27, a 240 volt single phase induction motor and a capacitor as static compensation are connected in parallel. The motor draws 9.3 amps at 44 degrees lag and the capacitor draws 5.2 amps. What is the supply current? So 240 volt single phase induction motor, got a capacitor in parallel. The motor draws 9.3 amps at 44. The capacitor draws 5.2 amps. What's the current? So pause the video here while you have a think about that, note it out and do the calc. Okay, we're back again. So let's now move on to the hint. So there are two ways to do this problem. You could draw a phasor diagram and do it reasonably accurately and to scale, or you could use trigonometry to find the lengths of the internals of the triangles, but you'd still have to draw a phasor diagram, you just wouldn't have to do it to scale. And then finally use some Pythagoras to determine the final total current. So if you haven't used either of those methods, have a think about that. Pause the video here. When you come back, we'll look at the answer. Well, welcome back. Let's have a look at the answer now. I've just very roughly drawn the phasor diagram. So I'll just change my pointer to the pen. So our capacitor, its current is directly up at 90 degrees. Here's our inductor at 9.3 amps at our 44 degrees. We were told it was 44 degrees lag. And we add those two together and we get this phasor in here, quite a shallow arrow. And we can then measure that length, scale it off our drawing and get our protractor out and get that angle theta inside there to give us the answer. Or we could use some trigonometry. So the first thing we'd need to find C, that's this little part in here, so this little bit here is C, and that's simply achieved by taking our 52, and we know the angle, and we can actually find B. So not too hard to find the length B, which is this one in here. So that's B. So we find B and we can just use trigonometry. Sine 44, 9.3 means that it's at 6.4 amps in length. So this is 6.4. And we know that the overall length is 5.2. So we take our 6.4 and subtract the 5.2. Should have drawn that all the way up there, shouldn't I? And we end up with our C being at about 1.2 amps. Next is we can calculate the length of A, which is this one in here. This is A. This is our length A in here. And again, it's just around this triangle. So we can use cos. We know that one side of the triangle, the hypotenuse is at 93, the angle's at 44, so it doesn't take much to work out that the length of A is 6.7. And so we have 6.7 and we have 1.2, so we can just use Pythagoras, and it tells us that it's 6.8 amps in length, and I admit I just estimated that it's about 6 degrees. Again, we could have used some trigonometry and worked out exactly what it is, but it looks like it's about 6 odd degrees. Next, question is 28. In relation to the power triangle below, which side of the triangle represents true power? So, which one is true power? Again, pause it here while you think about it. So you shouldn't have needed too much time for that. We'll go to hint, draw the power triangle. Just draw up the power triangle straight from your equation sheet even. So let's now move through to the answer. So true power is side B. So this side of the power triangle is the resistive component. So this is the resistive component. It's the true power all day, every day. This is the true power. So obviously at 90 degrees to that you get the reactive power, and the hypotenuse of the power triangle, of course, is the apparent power. Question 29. An electric induction motor has a rating of 26 kVA at a power factor of 0.85. What is the true power? So again, an electric induction motor has a rating of 26,000 VA or 26 kVA at a power factor of 0.85. What is the true power? So pause here and select your formulas, do your calc. Well, welcome back. Let's give you a little hint. So the hint is draw the phasor diagram and think how trigonometry can help you. So again, draw the phasor diagram or the power triangle, which is a phasor diagram, and think about how it can help you. So let's now move on to the answer. And again, here's our power triangle. The true power is this one down here, and it's calculated out at 22.1 kilowatts. And the way we did that is kVA. The first thing you needed to recognize is that VA, this one here, this is the apparent power. That's the first thing you need to recognize. Next, the power factor is the cos of the angle from the reference, the resistance here being the reference. And then it was just a simple matter of a little bit of trigonometry, and we were trying to calculate the total power. So it was simply 26 multiplied by 0.85. We already have the cos of the angle, and 21.1 kilowatts. So the true power is always going to be smaller than the apparent power. So you can do a double check on yourself when you do a calc like this, because you say to yourself, draw the power triangle. This side of the triangle has to be smaller than the hypotenuse. If it's not, then you've got to ask yourself, have I done something incorrectly? Okay, question 30. In relation to the power triangle below, which side of the triangle is measured in VAR? VAR. So again, we'll pause here. You just pause the video while you think about it. Well, welcome back. Let's have a quick look at the hint. So again, draw the power triangle and label the units that each one uses. That's going to be the hint, isn't it? What are the units? So let's now move on to the answer. And VAR stands for volts, amps, reactive. So VAR is volts, amps, reactive. And on this particular power triangle, here's our 90 degrees. The horizontal is our watts. The hypotenuse is our VA. And the angle opposite the power factor is the Q, the reactive power, and it's measured in VAR. So the answer was B, reactive power, measured in volts, amps, reactive, which we just abbreviate to VAR. So question 31 now. The following readings were taken around a piece of reactive electrical equipment. The voltmeter read 235 volts, the ammeter 6.2 amps, and a wattmeter 1244 watts. So determine the circuit's power factor, the phase angle, and the reactive power. So pause here while you select your formulas, think that through and do the calcs for three things. Well, welcome back to our last question. So what's going to be the hint? So here's the hint. Again, draw a phasor diagram, label it with the data from the question, and then answer it. So again, draw the phasor diagram, label it, put the data into the diagram, and then calc. All right, hopefully you've got to the right answers. So let's have a look at what those answers are. So here are the answers. If we were to do a phasor diagram, we can work out the cos of the angle because we can work out that the wattmeter is giving us true power. So here's our true power. We can work out our apparent power, our VA. Here's our VA. Work that out. Our 235 volts multiplied by our 6.2 amps is going to be our volt amps. So we've got 1457 VA. So now we have two sides of the triangle. So 1 and 2. We have the phase angle, so we can work out the phase angle simply by going cos to the -1 of the 0.85 ratio, and if you punch that into a calculator you should get 31.78. So close enough to 32 degrees. So 32 degrees is theta. And then finally we need to work out what the reactive component was. Remember they asked us for the reactive, the Q. So that's going to be the square root of 1,457 squared minus 1,244 squared, and that's going to give us 759 VAR. And again, can we check our answers? By doing the phasor diagram, we can see that the watts is a fair bit less than the VA. That makes sense. So by comparing those two, we can say to ourselves, yeah, tick, probably right. And we look at the Q, and the Q has to be less than the VA. Remember, the hypotenuse is always the longest length on the triangle. So it's got to be less than that. So we can do a comparison again this way, and it's a lot less. So again, we can probably be reasonably confident that we have got the right answer. So a couple of ways you can actually give yourself a bit of a check. So that's the end of part 3. Again, thanks for listening. Hope you've gained some improvement of your knowledge and skills around alternating current.